The majority of us know about the standard story of how the universe started. There was a boundlessly thick mark of a limitless temperature with no size, called a peculiarity. This peculiarity detonated, making all the space, energy, and matter that we consider to be our universe in an event called the Big Bang. Between 1, 0, minus 36, 10, minus 36 seconds and 1, 0, minus 32, 10, minus 32 seconds, space expanded dramatically, developing a whole lot bigger in size. Later, this period, space kept on extending, however, at a much slower rate. And at last, we see the universe that we notice today. This is the inflationary Big Bang theory, the most famous and extensively acknowledged theory of how the universe started. However, for a couple of physicists, the chief theory doesn't paint an exact image of the development of our universe. Maybe, they say that the universe existed before that point, extending always into the past as well as the future. While the universe is extending today, it was retracting in the time before the Big Bang. In this image, the Big Bang isn't so much a bang but a bounce. A second when a contracting universe turned around course and started to develop. As per their theory, the universe could bounce again. The present extension could be trailed by a collapse in the far future, followed by another bounce. A few physicists have suggested this bouncing could be limitless. This obviously is counter to the manner in which most cosmologists see it, where everything began with the Big Bang. However, what is noteworthy here is this isn't the only theory that really considers testing. The latest theory of cosmology, eminent physicist Brian Cox too, challenges the theory of the primordial Big Bang, declaring that something can't rise out of nothing. Adding a touch of strain, the James Webb Telescope has made a lot of unforeseen revelations that go against the idea that the Big Bang denoted the start of the universe. These bring up a question. If the Big Bang wasn't the start of the universe, then what was it? Might the universe at any point start with a bound or something completely different? Join us as we dive deep into one of the thorniest issues in physics. Did the universe have a start or a day without a yesterday, as it was initially known? This goes as far back as George Lemaitre in 1927. In spite of the fact that it's still a solid position to state that the universe probably had a beginning, that phase of our astronomical history has very little to do with the hot Big Bang that described our early universe. In spite of the fact that many laypeople and, surprisingly, a minority of experts still cling to the idea that the Big Bang implies the very start, all things considered, that definition is obsolete. The Big Bang now isn't the birth of existence we know today. In 2012, in fact, there's a lot of proof that points to a non-particular beginning of our universe. We won't ever reach those for random reasons, high temperatures, there's a cutoff. Rather, our universe is best described by an inflationary period that happened before the Big Bang, and the Big Bang is the consequence of what happened at the end of expansion. During expansion, the universe was totally empty. There were no particles, no photons, just void space itself. That empty space had a tremendous amount of energy in it at each location, with the specific amount of energy somewhat fluctuating over time by around 1 part in 30,000 on average. As the universe swells, growing in a quick, determined fashion, those fluctuations get extended to larger scales, while new small-scale variances are made. At top, this superposition of variances at small scales, at top transitional scales, and at top large scales is one of the defining predictive features of grandiose expansion. This goes on as long as expansion continues. However, expansion will come to an end arbitrarily and not in a uniform manner. In fact, if you lived in an inflating universe, you'd likely experience a nearby region where expansion came to an end while the space between you and it extended dramatically for a brief moment. You could even have the chance to identify what happened at the beginning of a Big Bang before that region vanished completely from view, in an initially somewhat small region, maybe no larger than a refined hamster ball, but maybe a lot bigger. The energy inherent to space gets converted into matter and radiation. The conversion process is relatively quick, taking roughly 1, 0, 33, 10, 33 seconds or so, a brief amount of time but still one that isn't immediate. As the energy bound up in space itself gets converted into particles, antiparticles, photons, and more, the temperature begins to quickly rise from just a few degrees above absolute zero to maybe 20 billion degrees or so over that same short period. Because the amount of energy that gets converted is so huge, everything will move near the speed of light. All quantum particles will act as radiation with so much kinetic energy intrinsic to them, whether or not the particles are massless or massive. It doesn't make any difference under these circumstances. This transformation process is known as reheating, and it marks the beginning of the hot Big Bang. As for the expansion rate, you'll observe a massive change from all previous behavior when the hot Big Bang first starts. In an inflationary universe, space extends dramatically, with more distant regions speeding away persistently. Yet, when expansion ends and the universe warms, and the hot Big Bang begins, more distant regions will now retreat from you to an ever-increasing extent, gradually over time. From an external viewpoint, the part of the universe where expansion ends sees the expansion rate drop, while the expanding areas surrounding it see no such drop. Under inflation, the distance to any object would double after a certain amount of time, and when that same amount of time elapses, that distance doubles again and over and over. The process is persistent. However, when the Big Bang starts, all that changes as the expanding universe quickly slows down. Once the initial moment of expansion slips by, it's very probable that, from the viewpoint of whatever region of inflating space you're in before the Big Bang, you'll experience expansion finishing off with adjacent regions. Normally, these places where expansion ends will rapidly fill up with matter, antimatter, and radiation, and expand more slowly than the still inflating regions do, leaving you in the inflating region as a typical region inside spacetime, dominating its volume. These regions where hot Big Bangs happen will extend away from the wide range of others where expansion continues dramatically, meaning they will very quickly recede from each other's view. In the standard inflationary picture, due to this expansion rate change, there's almost no chance that any two universes where separate hot Big Bangs happen will ever collide or connect. Finally, the region where we will come to live gets infinitely fortunate and expansion ends for us. The energy that was inherent to space itself gets converted into a hot, dense, and nearly uniform ocean of particles. The only dominant fluctuations and the only deviations from uniformity relate to the quantum fluctuations that existed and were extended across the universe during expansion. The positive energy quantum fluctuations will relate to initially overdense regions, while the negative energy fluctuations get converted into initially underdense regions. However, that is still enough to serve as the seeds of grandiose structure. We can't observe these density changes today as they were at the point when the universe initially went through the hot Big Bang. There are no visual traces we can access from that early time. The first we've ever gotten to comes from 380,000 years later, after they've gone through countless interactions. Indeed, even then, we can extrapolate back what the initial density fluctuations were and find something incredibly predictable with the account of grandiose expansion. The temperature fluctuations that are imprinted on the first image of the universe, the cosmic microwave background, give us confirmation of how the Big Bang started. Anyway, there are a lot of irregularities between the cosmic microwave background and our current model of cosmology. We're missing something. These can be summed up in 4 anomalies. First, on extremely large scales, the universe isn't behaving like we think it should. Second, light from the cosmic microwave background will be lensed by intervening matter between us and the cosmic microwave background. This means that matter behaves like a massive lens, bending and altering the brightness of the light behind it. The amount that this happens isn't consistent with our current model of the universe. This is such a critical issue, it has sometimes been known as a crisis for cosmology. Third, the two sides of the cosmic microwave background sky have different average temperatures. This doesn't seem right since we believe that the universe should have begun uniform overall. And last, the value of the Hubble constant, which describes how fast the universe is expanding, is different whether we measure it from the cosmic microwave background or from closer by distant stars. Taken together, these anomalies mean we are missing something crucial in how we understand the universe. The answer might lie in loop quantum cosmology, LQC. Loop quantum cosmology emerges from loop quantum gravity, LQG. In loop quantum gravity itself, it's made of particles called quanta. These quanta come together to form the fabric of spacetime. In this model of the universe, there is a smallest size of space itself, the Planck scale, or 1, 0, minus 35, 10, minus 35 meters. Nothing, not even space itself, can be smaller than this, which implies that the Big Bang couldn't exist in a universe with loop quantum cosmology. the universe would never get down to a vastly small, infinitely dense point close to the Big Bang. When the universe was very small, very strange things occurred. Numerically, infinities began to emerge and threaten to tear the fabric of spacetime itself. It's at these places where loop quantum gravity can come in to provide corrections to the physics we already know. As Dr. Ushker has shown, one of the first proponents of loop quantum gravity, when these corrections are applied, the Big Bang singularity disappears. In its place is a cosmological bounce. Rather than coming from nothing, the universe can go through infinite cycles of expansion and contraction, all in a perfectly non-singular manner. This idea isn't entirely new. People have explored the possibility of a grand bounce for a long time. In Hindu cosmology, the universe is eternal, going through vast cycles of expansion and contraction. Yet this presents an issue. Each time the universe contracts, entropy or disorder increases. This is a statement of the second law of thermodynamics, which states that the universe we're in now is continuously getting less organized. After an infinite number of bounces, there wouldn't be any energy left to have anything like a universe at all. Yet this remains a powerful idea, and it shows the remarkable power of loop quantum cosmology. Finally, whether the universe had a start or is timeless remains a contentious debate in cosmology, shaped by ongoing discoveries and theoretical advances. Loop quantum cosmology, LQC, proposes a fundamental shift from the classical understanding of cosmology, especially regarding the origin and development of the universe. At the core of LQC lies the concept of quantum geometry, which suggests that spacetime itself has a discrete, granular structure at extremely small scales, on the order of the Planck length, 1, 0, minus 35, 10, minus 35 meters. This granularity prevents the existence of singularities, such as the infinitely dense point conjectured in the standard theory of primordial cosmic inflation. Instead of a singularity, LQC posits a bounce, where the universe undergoes a phase of contraction before rebounding and beginning to expand again. The idea of a bounce addresses some of the key issues in cosmology, including the origin of the universe and the nature of time itself. According to LQC, time can be traced back beyond the bounce, suggesting that the universe might have existed in some form before our current expanding phase. This idea challenges the notion of a singular beginning and opens up possibilities for a cyclic universe model, where expansion and contraction cycles could repeat indefinitely. One of the significant features of LQC is its ability to predict observable anomalies that deviate from standard cosmological expectations. For example, LQC provides insights into the behavior of the early universe that might explain anomalies in the cosmic microwave background, CMB, radiation, such as unexpected temperature variations or imbalances. These predictions offer testable hypotheses that could potentially reconcile discrepancies between theoretical models and observational data, providing a new framework for understanding the universe's origins and evolution. In addition to its implications for cosmology, LQC also intersects with quantum gravity, a theoretical framework attempting to unify general relativity and quantum mechanics. Unlike classical general relativity, which breaks down at singularities, LQC introduces quantum corrections that smooth out the fabric of spacetime under extreme conditions. This quantum smoothing not only addresses mathematical infinities but also suggests an entirely different narrative of cosmic history, where the universe emerges from a quantum state rather than a classical singularity. Furthermore, LQC incorporates insights from loop quantum gravity, LQG, which posits that spacetime is composed of discrete loops or networks akin to a fabric woven from quantum strings. These loops interconnect, defining the structure of spacetime on a microscopic scale. By applying LQG principles to cosmology, LQC bridges the gap between quantum theory and cosmological observations, offering a more comprehensive picture of the universe's evolution from its earliest moments to its current expansion. The theoretical framework of LQC continues to evolve with ongoing research and computational simulations exploring its implications for cosmic evolution. Researchers are actively investigating how LQC can account for the formation of structures in the universe, such as galaxies and clusters, and whether it could provide new insights into phenomena like dark matter and dark energy. In the end, while the Big Bang theory remains the prevailing model for the universe's origin, Alternative theories like loop quantum cosmology challenge conventional wisdom and offer new avenues for exploration. By integrating quantum principles with cosmological phenomena, LQC provides a fresh perspective on cosmic history and the fundamental nature of spacetime. Future observations and experiments, including advancements in astrophysical instrumentation and theoretical developments in quantum gravity, will continue to shape our understanding of the universe's origins and its ultimate fate.